The experimental results of the double slit experiment using monochromatic light are subtle to try and explain, because the pattern observed on the screen can be described using two wave phenomena, interference and diffraction. We'll work with the model of monochromatic light as a plane cylindrical wave to derive a mathematical relation that describes the intensity on the screen wall. For now, we won't worry about light being composed of particles like photons, or concern ourselves with questions about the light's true trajectory. For now, we will assume that light travels in cylindrical wavefronts to and from the slits with a constant velocity and address these points later. If we zoom in onto what happens after the light passes through the two slits, and we'll show the paths of the light rays travelling to a point on the screen. We'll say that the distance between the two slits is equal to d. And the distance of the point on the screen, y. And we'll say that the distance to the screen from the slits is x. Now, we make the assumption that since the distance between the two slits is very small compared to the distance from the slits to the screen, the geometrical light rays from both slits travelling to a specific point on the screen are parallel. For the moment, we'll not worry about the finite width of the slits, and we'll deal with this later. We see that in this model, the light from slit 2 has had to travel further than the light from slit 1. This means that when the waves from each slit meet on the screen, there will be a phase difference between each wave. So to find out where the bright and dark fringes are on the screen, we can use the knowledge of superposition of two waves, shown here, to note that when the path difference is an integral number of wavelengths, we observe constructive interference, and when it is a half integral number of wavelengths, we observe deconstructive interference. By looking at our diagram from earlier, we can see that the path difference r2 minus r1 is just d sine theta. Hence we can write both our conditions for the light and dark fringes. Using equation 1, and the knowledge that the distances from the centre of the pattern to the nth bright band ym are much smaller than the distance x between the slits and the screen, we can write an expression for the position of the nth bright band on the screen. The intensity distribution on the screen, owing just to interference effects, contains a cosine squared term and looks like this. Here it is graphed. We can see from the experimental results that this isn't the right intensity description. As we see within the bright bands, there are subsequent dark bands. This is because we've yet to include the effects of diffraction. Diffraction is the term given to the phenomenon of waves spreading out after passing through an aperture. It is described well using Huygens' principle, stating that we can treat every point on a wavefront as a source of secondary wavelets, whose envelope at a later time gives us the wavefront at that later time. Let's apply this to the one-slit setup to see how diffraction comes into play. Again, we're making the assumption that the distance from the slit to the screen is much larger than the slit width, A. Let's look a little more closely at how this works in just the one-slit experiment. Again, we subdivide up the slit into multiple different points that are each emitting wavelets. We have one at the centre of the slit. And again, let's zoom into this situation here. We can once again take the assumption that the rays are parallel, as the slit width A is far smaller than the distance from the slits to the screen X. So we find that a dark fringe occurs when the path difference, now A over 2 sine theta, is equal to half a wavelength. We can now rearrange this for sine theta. These assumptions allow us to find the intensity distribution of diffraction from a single slit. Which is plotted here. We notice that the angular position on the screen is inversely proportional to the slit width if the angle is small enough. This is an example of the momentum position uncertainty principle in action. When we try to localize the position of the light, we find that the vertical momentum spread of the light increases. So when we piece together both diffraction and interference effects, we get a final expression for the intensity. This intensity function models the experimental results very well.